So let's get started here. Today we have some real work to do. Most of that code, certainly calculating that process table command that gave all the information properties when you passed in an epsilon machine. There's a lot of technology built into the computation mechanics and Python library. And today's lecture and Thursday's lecture are going to give you some sense of how things go. And I'll try to indicate some of the problems that confront you if you want to calculate these informational quantities from an epsilon machine, or just in general, how do you estimate them from a given presentation of a process. So far, the way we've been discussing things, we've been talking about the epsilon machines, in particular focusing on the predictive equivalence relation, the causal state equivalence relation, which gave us these partitions of the space of histories, so-called causal states. And as we emphasize, we talk about the intrinsic semantics that a model like that gives. These causal states were conditions of knowledge about the past that let you do optimal predictions of the future. Okay. Well, that's just the tip of the iceberg in this computation mechanics setting. So what I'm going to introduce today is actually tantamount to a hierarchy of states of optimal prediction. Now, the language will largely focus on different kinds of models or presentations, different kinds of states. But in fact, it's sort of a quite general idea. In other words, the original predictive equivalence relation actually induces conditions of knowledge for optimal prediction, but it's sort of conditions of knowledge for prediction. It actually telescopes out. We're only going to go up one level. That's all that's really necessary for most of the things we're dealing with, until we get to infinite state processes, and then it kind of is unavoidable. So there's some mathematical heavy lifting to do to introduce this. I'm hoping the gods of clarity will smile on me as I explain some of the technical difficulties, but there'll be examples. And in fact, just as kind of a heads up, think back to the Tahitian vacation example, where you're talking about reading the newspaper, getting forecasts, and trying to infer what the state of the weather was on Tahiti before we hopped on the plane and packed our bags. It's one way to think about this is this notion of synchronization we've been talking about. It's like a key idea here. It helps organize a lot of the constructions. We have some observations. There can be a setting in which we have a model, but we don't know what the current state is, and we're trying to guess what that is. So that's kind of the overall mathematical setting. Do a little bit of review today, mostly kind of notational things, but it's a little bit subtle. We're going to talk about conditional probabilities and also conditional random variables. We need to condition on things like, what is the current state distribution, or what was the state distribution when the process started? So I have to be more explicit about that. I hope it ends up being intuitive. We kind of dive down to a level of notational detail that I hope will asymptotically be helpful. Then with this sort of behind us, we'll start talking about this new concept of state, so-called mixed states, and the induced model, mixed state presentations. And we'll go through some examples. Then on Thursday, we get to have more fun. We actually get to see the benefit of using this mixed state presentation. So not only are we introducing this new concept of state, and it has a number of direct consequences. In particular, how we can very efficiently calculate these various complexity measures, and I'll talk in some detail about fast ways of calculating block entropies. And we'll do just a revisit the synchronization information and rewrite things in a very efficient way. And then This will give you some sense of what's inside the computation mechanics in Python package. In particular, right, there's a problem here. You know, if you have some kind of stochastic process, you're looking at words of length L. If it's having slightly positive entropy rate, the number of sequences that you can see of length L grows exponentially in L. So that's an exponential number of numbers you have to keep track of. And makes estimating word distributions quite problematic, especially if you're trying to do it literally from data. Take a window of length L and sweep it through and just counting things up. In many ways, one of the punchlines here is going to be, this is why we build models, because we need more efficient ways of estimating quantities than the sort of literal frequency counting of words. So we'll see how this mixed state presentation leads to a very efficient way of calculating block entropies and then other quantities that depend on the block entropies. Next week, we're going to get back to this question of we brought up last week. We were having to talk about the processes in reverse. We didn't really know how to think about it other than just state the intuitive idea that we're scanning the random variables in the opposite direction. And the question came up, well, if I have an epsilon machine that produces a process, well, I can certainly produce the process and then scan it in the opposite direction and then build the epsilon machine. But is there some way of just getting the reverse epsilon machine from the forward one directly? And it turns out this mixed state presentation is key. So next week, we'll talk about using mixed state presentations to reverse a process. And that turns out to be, well, kind of interesting in its own right and also leads to efficient calculation of a whole nother batch of complexity measures, including, somewhat surprisingly, this time symmetric quantity, the excess entropy. So anyway, I'm giving sort of a heads up here because, well, you'll see why I'm giving a heads up. Sleeves up. Okay, so review. Golden mean, process, right? No consecutive zeros. If you see a 1, the next symbol is a fair coin flip, 0 or 1. This epsilon machine has 2 states. We have this binary alphabet, all very familiar. We have our matrix that gives the transitions on 0 symbols, the matrix that gives it all the transitions on 1 symbols. Just one transition here from A to B with probably a half on symbol 0. Here we have 2 transitions from A and B to A. If I'm B with probably 1, I go to A. If I'm in A, probably half, I come back to A. Should all be very familiar by now. If we're interested in the internal state process, we just sum over, just component-wise sum these symbol-labeled transition matrices and get the internal Markov chain transition matrix. If we solve for this eigenvalue equation, doing left multiplication here, normalizing pi and probability, we get the asymptotic state probabilities. Okay, so that's all very familiar. Okay. Most of the time we spend in state A. Yeah, Chris.
Can I ask you a question that could probably take a quick answer? I'm
Sure.
curious, this should generalize to more than 2 states, right? Or binary.
Oh, sure. Yeah, arbitrary.
Are there any tricks to that other than just you have more than just T0 and T1?
Oh, yeah. I'll talk about some processes that have, I'm going to turn up the volume here in your speaker. Yeah, you can have, I mean, I would say right now, a finite measurement alphabet. It's easy to handle. We did talk about some infinite state processes, but yeah, this can generalize a little bit. Extending this all to, say, where the output was a continuous variable, that's the research frontier. Yeah, just trying to be concrete here with the golden mean. And then if we think of now the golden mean epsilon machine as a generator, like you might have noticed every once in a while, the edge labels, sometimes I put the transition probability on the left side with the output symbol on the right, or vice versa. There are actually 2 modes of using these epsilon machines. One is in this mode, transition probability output. We think of this as a generator. I have the model and I want to generate the realizations. And then when it's the other way around, we think of it as a recognizer. It's reading in zeros and ones, calculating path. The machine is calculating path probabilities. minor difference here. So here we've got this, and the question is, well, what words does it produce, and what are their probabilities? And we calculate the word distribution this way. So we start with asymptotic invariant distribution. We have its product of the T01 matrices extended to words, and then we sum things up with this column 1 vector. And that'll give us the probability of a word. Simple case, what's the probability of seeing a 0? So we have 2/3, 1/3 for the state probabilities times T0. And then we sum things up. Well, okay, so we're starting here with 2/3, 1/3, and then we see a 0. Well, we're in state A with probability 2/3, and we're going to see a 0 with probability half, so that's a contribution of 1/3. We're in state B, probability 1/3, but we can't see a 0. So the probability of seeing a 0 is 1/3. Same thing here, probability of seeing a 1 is just pi times T1. Well, I'm here with probability 2/3. I can see a 1 with probability half, so that's 1/3 contribution. I'm in state B with probability 1/3, but I'm going to see a 1 with probability 1. So that means I have a third and a third contribution, so the probability of seeing a 1 is 2/3, and so on. Okay, I'm going a little sort of pedantically here, and we calculate these things this way. I mean, this is already sort of showing you what I said before. If I wanted to calculate the probability of all the length 10 words, I'm going to have 2 to the 10 or 1,000 of these calculations to do. Tedious. Okay. So, just notation for probability theory. We're going to have our discrete alphabet. Now we're just thinking of processes. We have a random variable time t, big X sub t. The instance of that, some value in the alphabet. Time t, lowercase, means particular value. And the way we think about this is this random variable, x of t, it's distributed according to this, or in the covariant-Thomas notation, it's just simply to say tilde. Random variable is distributed as this distribution. We're going to use this a lot. Okay. We have different types of random variables, quantitative or categorical, age, voltage, temperature, whatever. Fine, that sort of makes sense. I can calculate the average age of people in the room or the average voltage in the circuit over an hour in my office. Categorical things, names, colors, I don't quite know. But we still talk about, you know, the probability of being sunny, but does it make sense to calculate an expectation value of the weather? No. Yeah, probably sunny and probably, you know, it's sunny in California, it's rainy in Tokyo, and therefore the expectation value is it's fog on Earth. I mean, it somehow doesn't, for categorical variables, doesn't really make sense. Expectation value of colors. Well, if you make the categorical variable red an RGB triplet or HSV triplet, then we can start talking about an average vector in color space. But until you make it quantitative, expectation values are a little bit sort of puzzling for categorical random variables. For processes, we have our observed process, right? This giant joint distribution of the bi-infinite chain of random variables. Typically, we assume that all the marginals of this are time independent. The probabilities are time independent, therefore it's stationary. At a minimum, the epsilon machine is some sort of convenient representation of the process, but that's just one. There are alternatives. So we choose these alternatives based on how useful they are. And then given the epsilon machine, we can at least calculate the word distributions using this simple formula, vector matrix multiply. Now, we've been sort of focusing on just the observed process this way, and we need to be more careful. So really what's going on, especially if we have, imagine we have the model, it's a little generator, and it's generating zeros and ones that we observe, but then the states are changing. So really, the observed process, or zeros and ones, or whatever alphabet, the words over whatever alphabet, it's really a marginal distribution from the machine process, which is pairs of internal state, output symbol, and so on. And we project onto just the measurement symbols when we talk about the process. But what the states are is actually important, obviously. And so it's been, when we've been writing down something like this, it's been implied that we use the asymptotic invariant distribution. And the benefit of that is that then these word probabilities are stationary. Their probability is the same anywhere in time. But that doesn't mean we always have to do that. We could use other state distributions. And the only cost is that then maybe these word probabilities depend on time, or the observed process is non-stationary. But we can certainly do that. So anyway, punchline is we're going to be a little more careful when we start to write down the word distribution like this. We're going to write out explicitly that it is an explicit average over state probabilities. Right? So what's the probability given that I started in a given state of seeing a word? So we go to each state, does it produce W? Next state does it produce W? And then we add up those probabilities. And that's what we mean by this. That the machine or process could have generated the word starting from any state. Okay, so this is just review. Some sort of computational things to note. So let's just say we have our state set V here. As I noted before, the number of words we're having to deal with grows exponentially with the length. So that's sort of burdensome. Is there a more efficient way to calculate these word distributions when we do this expression here? And the answer is yes. So the kind of straightforward and inefficient way is, so here, we're asking for what's the probability of seeing the word ABC. And again, just applying the formula, that's pi, TA, TB, TC. And then we sum up with the unit vector. And if you just sort of write it out explicitly, you have to sum over all possible paths that could have produced A, B, or C. Okay, so that means the sum here is the number of terms we have. Each one of these variables goes over the number of states. The longer the word, we have another set of states we have to sum over, and so the number of paths grows exponentially with this. So that's bad. So this first method here, just multiplying these things out, it's taking into account, it's calculating the probability of this word over all possible paths. And that grows exponentially in the state size. So that's not so great. However, if you just a little bit of careful thought, and probably if one was programming this up, just the very fact it's so inefficient would lead you to think about grouping things in a different way. So the second way, which is completely equivalent to the first, is that every time we look at a new symbol from the word, we update, in a sense, summarize what's happened in the past by just pushing the state distribution forward with that single matrix. Well, that's a vector times a matrix. That's nice. And then now I have a new state distribution. Then I just go state distribution and I update it with, in this case, the B matrix, new state distributions. Okay, I have now 3 matrix multiplies. If it was length L, I'd have L matrix multiplies. Therefore, the second way of doing it is actually linear in the length. We're actually using the states to carry what we need from the past. We don't just throw all the paths out there and figure out which are the probability that they assign to ABC. We do this nested updating of the internal state distribution. Again, it's just like the synchronization problem. Oh, sunny, rain, and you're updating your distribution of the internal state of the diffusion weather system. Right, so now we have this vector here, and then the sigma component of that is the probability that you produced W and ended up in state sigma. And then we just keep pushing that forward. So bad, good. So rather than having your calculations sort of poop out on you, it's short word lengths, you can push this quite a lot further. Okay, so now, really terrible colors. Right, so conditional probabilities, the way we've been thinking about them. Right, what's the weather on Tahiti if I read in the paper that it rained yesterday? So we think of conditional probabilities, we've been conditioning on events. Well, we have to modify that a bit. Why? Because what I was just talking about is we're conditioning on knowledge of the state, and that's a distribution. Actually, we're going to think of that as a random variable. So, but that's okay. You know, these conditional distributions, they're still distributions. We know how to work with them. But we're going to need some notation to deal with conditional random variables. So what we mean by that, and I hope the notation will bring this across. So we have this two-letter alphabet, AB, and a random variable x. And I'm going to define a new random variable that represents the distribution of, namely the probabilities that x0 is A or x0 is B. Okay, so and what I mean here is that there's going to be this sort of hidden variable. I'm wondering how A and B are being produced depending upon what the current state is here. So this is going to be the probability that x0 is A or B conditioned on a particular state. So, and so in a way, this notation will let me sort of, like occasionally sort of hide, hopefully not obscure the fact that we're depending on this condition. Also, there's a sort of an ambiguity here in when we look at entropy notation. So the entropy of this new random variable is, it's conditioned on the value that this S state takes. And it's not the same thing as the uncertainty in the variable x0 given the previous state, because this entropy we average over all possible states. Right? So this is a random variable that is the value, describes the probability of seeing x given on a particular condition that is fixed. So here's one example of this. So here we have our machine process here, state symbol, state symbol, state symbol, so on, okay, going forward in time. And I define a new random variable, call it J0, that's distributed according to how the probability of x0 is conditioned on S0 being A. So this random variable is distributed according to the conditional probability of x0 given S0 is a particular value. So imagine that we're asking this is produced by the even process. So, and I sort of changed this here. Instead of zeros and ones, we have triangles and squares. So this is the even triangle process. So what's the probability that J0 is equal to a triangle? Well, what is that probability here? Well, just by the way we've defined it, probably that J0 is a triangle is the probability that x0 is a triangle, given that S0 was state A. Okay, so given that we're in state A, what's the probability of seeing a triangle? A half. And that's not the same thing as just asking for what the probability of x0 is when it's equal to a triangle. Right, that is this product here. Yeah?
So question then about conditional. So would J0 even exist if S0 wasn't A?
No, it's defined this way. Right, I'm defining this. I could make Q0 be S0 is B, and I have this new random variable.
I guess it's
right.
just throwing me off that the random variable kind of isn't even, it depends on S0.
Yeah, right. So I'm kind of, right, I'm trying to describe, right. So this is a random variable that's described by not a distribution, but a conditional distribution. I'm calling it a conditional random variable. And it's related to the event set X, but now the event set X is being partitioned up by this other state variable here in this case.
Yeah.
Yeah. Right. So this down here, this probability, it's just, when is x0 a triangle? Well, I'm here 2/3 of the time, I see a triangle half the time. I'm here 1/3 of the time, I see triangle with probability 1. So that's 2/3 times a half, that's 1/3. 1/3 times 1, then I end up with 2/3 again, just like before. Okay, so that's straightforward. And these are various constructions we'll use. Maybe it'll be a little more intuitive when we get to the examples. Another example would be defining this conditional random variable f2, that's the probability of being in state 2 given that back at time 0 I started in sigma 0. So what's the probability of that? F2 is describing the probability of ending up here, or I should say my uncertainty in here, given that I started over here in a particular state. Call it A or B. Okay, so now I can condition on this. Right, so the point here is I need to be able to talk about sort of telescoping conditions. So what's the probability that x2 is equal to a particular value, triangle or square, given that f2 was sigma 2? In other words, and what that means is, we'll just unpack that. I'm going to rewrite f2 here out explicitly. It's this conditional random variable, and now I'm saying that f2 is equal to sigma 2. That means this first variable here, it takes on that value. So now I have this conditional random variable that's s2 is equal to sigma 2. Here I end up in sigma 2. When I started here in sigma 0, well, that's fine. We can just drop the conditioning here. These are just events. Same thing as the joint event. S2 was sigma 2 and S0 was sigma 0. Okay. I just unpack that there, but then we can simplify this, of course, because we're using these causal states. And shielding means I only have to worry about the immediately preceding state, so I can simplify that. So this is just kind of example calculation. I'm interested in this condition up here, and later on these are going to turn into distributions over states like this. And in this particular case, the uncertainty in x2, given that f2 was sigma 2, this value up here, it's the same thing as asking about x2, given that that state was actually sigma 2. So this f2 variable sort of collapses down because of shielding to being equivalent to asking about the state at time 2. Okay, so just to draw a contrast here, so we just established we had this probability identity, and then also down at the level of the information, the uncertainty condition either on F2 or S2. Those are the same. However, when we talk about, without conditioning this way, we just talked about, well, what's the uncertainty in X2 given F2, without fixing it. That means we're averaging over the realizations of F2 this conditional entropy. That's just sort of the standard definition of that. Right, but now I can sort of unpack this a little bit. This is this conditional random variable over S2 and S0 fixed at sigma 2 and sigma 0. But that's not the same thing as the uncertainty in X2 given S2. Right? This we only would condition over the value of S2. We would have suppressed this condition that was built into F2. So these two quantities needn't be the same because F2 has built in this, I guess, sort of hidden condition. Okay, I guess sort of a final example here. Right, so G2 is the probability of our uncertainty in S2 given that X2 had a particular value. Okay, so we're sort of, given that we saw this observed symbol, we induce a conditional distribution over the previous state we could have been in. And now I'm going to ask a question about the probability of the next state. I'm just kind of making these up to show the different instructions here. So that's probability of S3 given G2, then these are fixed. So then since G2 is now being fixed at sigma 2, that means that this first variable is being set to sigma 2. So I just rewrite this again. Probability of S3 given now this conditional random variable, I just break it out into the separate events. It's now a joint event, right? And then you even say something noted down here. If given that S2 is fixed and X2 is fixed, if this was an epsilon machine, then the probability would be 0 or 1 whether I was going to sigma 3 at time 3, depending upon whether that was allowed or disallowed transition. Okay. Same thing with the there's the entropic version of this, the uncertainty in S3, given that G2, this conditional random variable, sigma 2, again, that's just simply this. Conditional distribution, it would be 0 if the machine was unifilar. Generally, again, just applying the straight definition, if I was interested in the uncertainty in S3 given G2 without it being fixed, then I'm averaging over the conditions realizations, this conditional entropy, right? The uncertainty in S3 given the different realizations or possible values of G2. Again, unpack this again, we have this conditional random variable, its probability. We got this above here, this number conditioned on this joint event, sigma 2, x2. And that's generally not the same thing as the uncertainty in S3 given the state distribution S2 and that we fixed x2 to be a particular value. Again, it's because of we have this hidden condition here. Okay, so these nested conditions have a certain syntax and meaning to them, but you just sort of unpack them till you just have everything be an event, and then we're back into the realm of sort of normal probabilities. So what does this generally look like? If we have this conditional random variable A prime, probably of A, given that B was little b, then we can talk about the uncertainty in some third event C, given that A prime was equal to A. And what we mean by that is now we fixed this conditional distribution so that the thing that's being conditioned takes a particular value. So this is just now a single number, as it were. And then the way we're conditioning the random variable on this conditional random variable turns out to be just the uncertainty in C given A and B. And that's different from if we don't fix the conditional random variable, right? So that's just rewriting the definition of A prime. It's the uncertainty in C given conditional event A given little b, which if you sort of write that out, that's now we're averaging over this random variable, although it's one component is fixed at B, and then we average over the values that A could take in the conditional random variable, and then that's weighting the conditional uncertainty in C given the conditional random variable. And again, sort of, and the third form of this is just looking at the uncertainty of comparing. We have this last conditional entropy on C given A and B, this sort of joint event. And that's different than if we haven't fixed A. Again, what we mean here in the definition of this conditional uncertainty is that the random variables that are not fixed are the things we sum over, that we use to weight the conditional entropy. Okay, so now getting back to where we're going to use this conditional random variable notation. Again, we're interested in the word distribution, and now we're being careful to be clear that it depends on the state distribution as we produce the word. So before we were just conditioning on events, and now we are sort of conditioning on these state distributions when we calculate word probabilities and entropies. And we have to make this dependence on the state explicit. And I guess it's natural enough if we think of this as a generator. And this, if you look at this expression, it sort of looks like, well, you're doing the state average of something. It kind of looks like an expectation value. So we could think of this as like an instance of a random variable, or if you like, conflate it to think of it as like an event. It's like a temperature. Well, it's a number, and we're averaging this number over the states. Okay, so this is, I guess, it's sort of this funny semantic shift here. I mean, to make this explicit, you could imagine we just come up with, define this sort of random variable, I should say distributed as, this conditional distribution, right? And so the values that this random variable takes are the probabilities that the word is W if you started in A or you started in B. Right? Could be 2/3, 1/3, and that would be the values of Z. Then the probability of Z taking a particular value, 2/3 or 1/3. Well, just plug in the probability that Z is actually equals that probability, and that just depends on what state you visit. Right? Everything that's driving it here is what state you're in. If you're in state A, I have this probability. If I'm in state B, I have this probability. So in fact, this does look like sort of an average. If I average Z over its distribution, so Z here, averaging over the different values it can take, the probability that those values occur, and you end up back with that original expression. So this is the way of thinking about how calculating these word probabilities conditioned on the state. It's as if we're averaging these numbers over these events over the state probabilities. But that's, I don't know, maybe this is over tedious or kind of flogging a dead horse. We could just sort of, by definition, just kind of agree to start conditioning on the state distribution here so that these averages over these numbers that we're interested in, these state probabilities, right? I want to know over which state I could produce the word, have its probability, and then we weight those by the state probabilities. Okay, so the other thing we're going to do is think back to that calculating, updating the state probabilities. We're calculating the word distributions. We're going to think of the random variable as actually being a vector of probabilities over the states. So for example, for the word probabilities, so now we can ask about what's the probability of producing a word, given that it says the states starting at time t are distributed according to the asymptotic stationary measure. That's just this formula here, right? And now imagine we didn't sort of sum this up. This is actually a vector of probabilities, or we can now think of this as the random variable we were just averaging over the states. Okay, but we can also talk about other distributions besides pi, right? Imagine it's a uniform distribution. Then the probability of seeing these words starting with the uniform distribution is just simply the sum, since all of these states are equally likely. We just have the factor of 1 over the number of states, and we just then sum up these conditional probabilities, having produced the word, or just in general, right? We can now start talking about probably producing words when the states are just given by some arbitrary initial state distribution. And then we just generalize our expression here. Just left multiply by mu, tw, and then sum up. So this notation it's okay. It's trying to make explicit what has been implicit before. So, right, so this is, right, what's the probability of x takes on value? Little x, given this state. Now this is just sort of the random variable, or we can also be clear how it's distributed. We can put in the distribution there. So these are probabilities, right? This is the probability that x1 is equal to x. That's a number. That's a number, okay? And then we can also work with distributions the same way, right? Now we can condition on both S1 and S1 given a particular distribution, and then this is a set of numbers. All the possible probabilities that x can take for its realizations. It gets a little bit dicey, though, when we're working with entropies. It's a little bit ambiguous. I mean, typically what we mean by the uncertainty of the next symbol given the current state is we're going to do a state average of the uncertainty in the next symbol for each state. Right? So that's just state average in some sense, the branching uncertainty here from each state, conditional entropy. And or in simplified form, it's just that we always put the joint distribution out in front of the log, and then the argument of the log is the particular kind of entropy we're looking at, in this case, symbol state conditional entropy. But there's also sort of possible when we write the same notation down that we could have meant with now thinking about these conditional random variables that this is the entropy over this conditioned random variable. So now I've got this p log p expression I'm applying to this conditioned random variable that x1 is equal to x conditioned on s1 in both places there. But if you work this through, you see there's this ambiguity. We could just sort of unpack this here. Right, this probability is the probability that we're going to see. So here we're averaging over x, values of x, and then also over the states here. That's what this conditional probability is, just the probability of we're averaging over the states here, but that we're conditioning on. So we pull out the state probability and multiply that, weight the conditional probability of x given sigma. And then we do the same thing in here, same expression, but notice that now this just turns into the joint distribution in both places. And this is a different expression than this one. So there are ways that in this new notation that we have to be careful. We can't unpack things certain ways, in particular this way doesn't quite work. So the first thing is just the average entropy of this variable conditioned on the events, all the state events, x. This one down here, the way we're thinking about this is the entropy of this variable for different S1 distributions. And it leads to this sort of confusing alternative. Right? In fact, this is just the marginal distribution over x. Marginal distribution over x. In some sense, so we have to be careful with that. So what we're going to do is, when we write this down, we'll mean the first thing, the average entropy of x1 conditioned on the state events. And then when we want to talk about averaging over particular distributions, then we're going to put in how the conditioning random variable is distributed. So, right, so this later thing, like the last example, just reduced to entropy in the first variable, something was not what we intended. But now, with this new notation, we can be explicit about what we're conditioning on. And of course, we recover, when mu is equal to pi, the quantities we were using before, namely the asymptotic invariant measure. The important thing about this is now we can start looking at how uncertainty is changing if we start with different state distributions. In particular, we're going to be updating these distributions as we go along. So we need to be very explicit about the state distributions we're conditioning on. Maybe that's kind of the main point of this somewhat tortured notational description. Okay, so for example, odd process. So this generates 1, 1, or 3 1s, and then a 0. So just it's the odd analog of the even process. The asymptotic distribution is 2/5, 2/5, 1/5 here, ABC. And we can ask about what's the probability at time 3 that we see a 0, given that at time 3 we were in state A, and the initial state distribution was distributed according to pi. Okay, and that's a question. Okay, so what does that mean, given how we've developed this? Well, first of all, this is this random variable is distributed according to distribution. That means we're going to average over it using its weights, right? Times 0, what state probability we had, those. And then, well, of course, this is like a previous example. Because of causal shielding, we can actually, this probability here, conditional probability here, seeing 0 at time 3 doesn't depend on what the start state probability was. It just depends on the immediately preceding state. So we can drop that. But now we're still sort of averaging over, right? We're carrying forward that state distribution. But notice now, this probability doesn't depend on sigma, what the start state was. You pull that out, and then we're just summing this distribution over sigma. Well, that's 1. So we end up basically showing that in this case, we forget the initial distribution. It only depends on the previous state. And that is, right, time 3, I'm in A, what's the probability of seeing 0? A half. Okay. Yeah. But we can choose a different state distribution and ask a similar question. So this, right? So imagine that we have mu just defined to be uniform probability over states A, B, C, and we want to know what the probability of, the next symbol at time 3 is, given that, say, at time 1, that was the distribution of state probabilities. Okay. So, well, we know how to calculate this. We can just take mu, push it forward 3 time steps. In the last step, we use the symbol transition matrix that produces the symbol we're asking about, and then sum that up. Right? Remember, and here we just can use t, because all we really need to do is to update the state distribution. Nothing. The first 2 steps, we're not asking anything about the observed symbols. Right? So that's the same thing as, this probability here is the same thing as, instead of S1 at time 1 being distributed as mu, we can look at S2 being distributed as mu t. We just pushed it forward. Or at time 3, it was mu tt. So we pushed it forward another step. And that's easier to answer. Here I can go out to step 3 and say, oh, that's my current state distribution. I can go to the states and then just look 1 step ahead, rather than sort of think about this extended over 3 time steps. In this, the only thing that's really important is the relative time difference. So here I was specifying mu at time 1 and looking at 2 steps later at the observed symbol. I could have specified mu at time 2 and looked up at time 4 for x, so that we can shift that way. But you can't just shift this random variable here forward when mu is not the asymptotic state distribution. When mu is, well, then as I'm operating on it, I just get mu back. I mean, get pi back. So then that'll be stationary. So you can't just shift this variable around. Why isn't that turning red? Odd. This thing must be missing colors. Okay, so yeah. So what are the shorthands we have here? So I write down the probability that at time t we see little x, conditioned at being on a state at time t. What this is a set of numbers, the size of which is the number of states. And each of those numbers is the probability that you're going to see little x for each one of the states, right? Whereas if I don't fix one of the random variables, then this is now a larger set of numbers, namely the probability that we see little x for the pairs c little x and c state sigma. Okay. Right, so now when we talk about what these numbers mean, right, we're thinking of this as the average number, average likelihood we're going to see x, but averaged over the state probabilities, right? So that would be the expected probability when we write this, expected probability, right? Or if we're not fixing the variable that's being conditioned, what we mean is the distribution over this. It's the expected distribution, right? So up here we had these numbers, 1 for each state. And down here we have a distribution that is now, we have a distribution for each state we could be in. So it's 4 different things. And then we average over the states, each one of those numbers, and we end up with a distribution over x. Okay. So hopefully, as we go forward, context will help us get rid of any ambiguity here. Either we can think of sets of numbers, sets of conditional probabilities, or expected probability or expected distribution. Okay, so enough of that. Right. So here's an example process. I should say this is a presentation that generates a process. It happens to be the epsilon machine for that process. And we have a fair coin flip from A, and then no matter what, we come from B or C back to A. So it's almost kind of like a period 2 thing, except when we go from C back to A, we flip a coin and generate 0, 1. Coming back from B, we generate a 0 with probability 1. So the way to think about the problem is that we know the model. So we took our data in our lab, but then we left for lunch. The experiment was still running. We come back and we don't know where it is. So we have the model, and we can, for example, calculate given the model, so our expectation, if we've been away for a while, is kind of in statistical equilibrium. So this is actually this vector here is pi, the asymptotic state distribution, a half, a quarter, and then the states colored in red here give the probability magnitudes. And so this is the state of affairs when you just walk back in the lab. We haven't seen anything yet. Okay, and this, a half, a quarter are our expectations if we assume equilibrium. So we got this one helpful way of thinking about this is looking at the time evolution of the state distributions. So this particular state distribution it's a normalized over 3 states, over 3 variables. Therefore, it's on a simplex, and all of the probabilities that sum to 1 and are between 0 and 1 lie in this triangle. So think of that as a 2-dimensional surface. This initial state distribution is over here. It's not much of B, not much of C, and about half of A. So half, a quarter. I should visualize this. Okay, so now what we'll do is read in a word and then talk through how our expectations of what hidden state the process is in get updated. Okay, so the first step will be we see a 1. Okay, so then looking at the model, we know there's no way to get to B on a 1. So there's no probability flowing over there. However, we started with probably 2/3 here, and probably 1 half here, 1/4 here. So on a 1, we take the half probability, and we take half of that and move it over here. So we now, on the next step, having seen a 1, we have 1/4 here. We had 1/4 probability before we saw anything, and then we took, seeing a 1, that takes a half of that, which is an 1/8, and moves it over here. So we end up with this partial distribution of 1/4 and an 1/8, which when you normalize it, makes the probability state C 2/3 and probability state A 1/3. Right, so you have an 1/8 and a 1/4, that's 3/8. Divide that vector distribution, an 1/8 and a 1/4 by 3/8, and you get 1/3, 2/3. And then our mixed state is updated. Now the mixed state lays along a sub-simplex, namely just the line, the 1-dimensional simplex between C and A, because there's no probability of being in B. So we're just along here. So on the edge of the simplex. So then we see, so we update our mixed state in this simplex, or we can think of it this way, on distribution on the states. We see another 1. We have a new mixed state here. So we had 2/3 here, 1/3 here. Half of 1/3 is a 6. We had 2/3. We take half of that, that's 1/3. So we have 1/3, 1/6. We normalize, we get 2/3, 1/3 again. Okay, then the red is the current mixed state having seen 1, 1. See another 1. It just happens to just swap these probabilities like this, but we have to go through the calculation again, which is just what we did before. And we come up and we can visit this same mixed state again. Okay. Now we'll see a 0. So now what happened is we had whatever was here, an A, it moves over here. We take just half of that probability mass, and whatever was at C, we move that over here. Okay, so that was, if I get the phase right on this, right, so 2/3, half of that is a 1/3, ends up at A. We had 1/3 here, take a half of that's a 6, so we have a 1/3 and a 6, and again it normalizes out, having seen the 0 to 2/3, 1/3. Now we can see another 0. Now what happens is that, in fact, having seen that our expectation is now 50-50 for B and C. You go through that calculation again. And then now we're down here, we can't B and C, so now we're in the subsimplex between A and B, and exactly 50-50, like that. And then on the next symbol, I'm just choosing allowed symbols as I like to illustrate things. The next symbol is a 1. And what happens is that now we had A and B with positive probability, but there's nothing leaving B on a 1, so that doesn't participate. We had this probability up here, and whatever it was, we take half of that down to here, but the C is the only one that has probability. When we normalize, we get this, call it delta function, right on C. The mixed state moves up to one of the vertices. Okay, so we get basically the kind of visual picture here of what it means to finally have synchronized. Now, having seen that sequence starting from state ignorance, we now know exactly what state we're in. So we call this a synchronizing word. There are words that will take you to this, if you have the right kind of presentation. This is a property, synchronization like this, a property of the model itself. We'll talk about some examples that don't synchronize. And then, because this particular presentation is unifilar, happens to be the epsilon machine, it's minimal, unifilar, every other, as I read more symbols that are allowed, I stay in the state of being synchronized. I never lose that. Again, that's one of the nice properties of unifilar presentations. It just kind of hops around now. And the dynamic on the simplex is just hopping between the vertices. Stochastically, because I'm sort of choosing the allowed transitions to take. So over to B after I see a 0, back to A if I see another 0, and so on. So we're kind of hopping around here stochastically on the simplex of state distributions. Okay, so that's the main idea, right? I made an assumption. We start in the asymptotic state distribution pi, and we're just trying to answer the question, how do we update our knowledge of the state? Okay. So maybe that's more intuitive than all this conditional random variable stuff, but actually that's, you're having to calculate with these things. So what are these mixed states? Okay, so in the simplex, we had these various dots here. Now we're thinking of the A, it's a random variable, or it's actually this point in the simplex that's hopping around. So two different representations of this to describe the evolution of our knowledge or uncertainty about the internal state as we're making measurements. So we have now some induced dynamic over this new kind of state space. Well, let's say state distribution space, the simplex. So that's what we want to track with these mixed states. That's basically what they are. So they're state distributions that are induced by having seen a word. So let's just look at words of length L. And then our notation here will be at time t, having seen no words, lambda in this case, will be in this mixed state mu. So we're going to come up with this more compact notation here of the mixed state at time t having seen some symbol or word. Okay. So what we're going to do is, this will be where we start. At time t, there'll be some state distribution mu having seen nothing. That's what that one means. Okay. So then, so now these, this is a random variable. Well, it's a state distribution. Well, it's a random variable. Okay. I think we're comfortable with it now, but there is some formal trickery here. So what's the probability of, at time t plus L, being in state sigma, given that we observed word W? Well, write this in more familiar notation, and this is where all the previous formal rigmarole. What we mean is the probability that the state at time t plus L is sigma, given that we saw word W going from time t to t plus L, that block, having started with this initial distribution, having seen nothing, and in that mixed state. Okay, so this is the general sort of way we're going to push distributions forward based on observing sequences. So then these mixed states really are random variables. They're hopping around. They're being driven by a random variable, namely the word that you're observing. They're conditioned on these two things. So the word and the mixed state, of course. And then typically, what we've been doing is just time is 0, and then this initial distribution we take to be the asymptotic distribution. But as we just saw, there are other questions one has where we use different mu's and push them forward. Okay, so the simple X picture is really based on thinking of now a different representation for the mixed states distributions as just vectors in some vector space. Right? If we have 3 states, it was a 2-dimensional sheet, and we can see how to calculate these state distributions. We just simply write out what we had before, right? It's the state that we're in at time t plus L, given we saw length L word, and started with this distribution. Well, that's a conditional distribution. I can write it as a joint distribution over a marginal. That's just a probability identity. And then we know how to calculate both of these. That's just given by our familiar formulas before. So now this is the way we can directly calculate, starting from a given mixed state at time t, and then going forward. Basically, this is what I was talking through in the example, and then that last normalization step is given by the denominator. Just to make, so this is some kind of partial distribution. I just push the state probabilities around on the model, and then I just make it a normalized distribution after that. And then, so now this sort of dynamic, I now know how to push mixed states forward, basically. And what we've been doing, of course, is just taking the asymptotic distribution pi times 0, we get this simpler expression. Just if we start with the asymptotic state distribution, we can calculate the mixed state having seen a word of length L, this way. So for the even process, just to focus in a little bit, we essentially did almost numerically the same example, but now we just have a 2-state process over triangles and squares. The even triangle process, we'll start the initial mixed state off in the asymptotic state distribution, 2/3 in A, 1/3 in B. And then the question is, what's the mixed state at time step 1 having seen a triangle? Well, that's the state distribution conditioned on having seen this past, namely triangle, and then we're now sort of denoting the and being explicit about the initial state distribution that at time 0 is distributed according to pi. So then we just push pi forward using t delta, and then we normalize it. So when you push it forward, right, we have 2/3, 1/3. Push it forward, having seen a delta, 2/3, half of that is a third. We had a third here before, and that moves to probability 1, so we take all of it over to here, so we get a third. So this is this partial distribution vector, and then we sum that up, well that's 2/3, and then we use that to normalize, and then we get half a half. So initially we start out with this, we've made this assumption, oh, it's been running for a long time, it's in statistical equilibrium, most likely in state A. As soon as I see a delta, I conclude that it's equally likely to be in either of these. So my state uncertainty can change over time until, in this case, we hit a synchronizing word, and then I would get the delta function, and there'd be no more state uncertainty. Start thinking about it's a new kind of dynamical system over these state spaces, these simplicial state spaces. These are just vector spaces. The vectors are these probability distributions. They're normalized. And we think about them on some simplex. So if we had 2 states, there'd be a 1-dimensional simplex, probability A, probability of B. There'd be this 1-dimensional space along which those probabilities between 0 and 1 and sum to 1. We have 3 states. That's what we were talking about before. We have this surface. And then over the surface, there's sort of, notable points. The vertices are what I call the delta function distributions. We know exactly what state we're in. The center point is always the state of maximum uncertainty. And then, all the other points, including the boundaries, are allowed. So if we're on one of the, you can think of, if arbitrary distributions over 3 states or just points here, but as we saw before, when we synchronized, or even before we can synchronize to a subspace, you can have distributions where you're not in some state, and that just collapses the dimension you're currently operating in. So what are these things? So they're just the uncertainty in the state, given some starting distribution and a word you've observed. We can look at the mixed state entropy, as a way of detecting whether or not we're in a state with probability 1. So this would be our informational criterion for being synchronized, right? So when the state distribution is all zeros except for 1, 1, then we know with probability 1 what state we're in. So we think of these mixed states with zero entropy as the sort of points of the vertices of the simplex. They're so-called pure states. And then all the other possible state distributions are spanned by those pure state vectors, and hence they're called mixtures of the pure states. Right? We can write an arbitrary state distribution in terms of these pure states. So it's very handy to just look at this geometrically. Also, and this is getting a little bit into the sort of the induced dynamic. We're sort of talking about the state space now. The induced dynamic is actually many to one. So in particular, you can have the same words lead to the same, different words lead to the same mixed state, right? So like we saw before here, we had 2/3, 1/3, and then after one step, seeing a triangle, we had 2/3, 1/3 here, and if I see two more, it just permutes it again. So either one triangle or three triangle word lead to that mixed state. So this mapping on the simplex going forward, I can have, for a given mixed state, any number of preimages. I shouldn't say any number, finite number of preimages. But okay, so the basic idea is that there's this sort of natural dynamic over words, right? That's just concatenation. I go from a word and I add something on here to make a new word. We have this equivalence relation between words now where they end up, when we're looking on the simplex, two different words can end up in the same mixed state. We think of, the mixed state is a state of state uncertainty. Hence the sort of hierarchical picture we give here. And then the dynamic that's induced over words, we have concatenation. And then for each one of these, we can ask, given that we specify the initial mixed state, what mixed state do I go to? I have a word that induces another mixed state. Then, and the way this diagram commutes, then there is a mapping from mixed state to mixed state on symbol. So, interestingly, this representation of mixed states, mixed state dynamic, is unifilar. Which means that, again, given the mixed state and the symbol, I go to unique next state. There may be many preimages, but there's always, I know exactly what state I'm going to, given the previous one and the symbol. Okay, so that was a lot of work. Yeah.
So is there some sort of mapping of this output process mixed state to the input process transient states?
Yes. In fact, I wasn't really distinguishing recurrent mixed state from transient mixed state, which we will next time. Yes. Good leading question. Yeah. Right. Yeah, exactly. So it's kind of right. So I mean, okay. Yeah. So what we've done here, we've moved from, and all the previous examples we have been talking is as if we had a probabilistic finite state machine, and we were talking about, I'm in this state or this state or this state. Well, okay. Sometimes we're not certain, and that came up a bunch. Now we've shifted up to this other picture where we have this dynamic over these mixed states, and we're tracking dynamically how our uncertainty in states shifting based on what we've observed. They're analogs to being synchronized or to being in the recurrent state of the epsilon machine at the vertices of the simplex when we have those delta function mixed states. But they're corresponding questions that we had before for the epsilon machine. Transient states, recurrent states, same thing comes up here. And we'll actually see that, for example, we can work with the transient states quite naturally, and it leads us, I'll give you a nice simple expression, kind of closed form expression for the synchronization information, the total uncertainty as we synchronize. And that's working just with the transient states, transient mixed states. But along the way, it turns out this is also kind of harkening back to when we're talking about the computational complexity of calculating the word distribution. There also lets us deal very handily with an efficient way of calculating block entropies and so on using the mixed states. Very efficient. So, okay, so that was a lot, or dense, I should say. So I'll finish unless there are questions. And we'll come back, and Thursday will be more application-driven. And you'll see some of this and why I had to bend over backwards to worry about some of the notation on Thursday.